Now the next part is a cache memory. When we use a cache memory, that lies between the main memory and the secondary memory, and the main advantage is that it is very fastest memory that is used with the three levels: registers, main memory, disk storage, that is available with this. And however, because of increasing gap between the CPU and the main memory, designers are compelled to make a small SRAM cache memory that is available, that is known as the L1 cache, level 1 cache, between the CPU register files and the main memory. And the L1 cache can be accessed nearly as fast as the registers, typically in the 2 to 4 clock cycles. And when the performance gap between the CPU and the main memory continued to increase, system designers may be reused or maybe asked to use the designer that is used with the L1 cache, that is used with between the registers, that is used between the main memory. And this is a diagram that shows how to use the main memory, how to use CPU registers, register files, that is used with the input-output bridge, main memory. Whatever the bridge that we are taking, that we are using, so that is available within the that is available within the CPU memory or the CPU. Now, CPU is, yes, central processing units. We require everything from the CPU because every processing is done by the CPU, so it's very mandatory to increase the size, and that is done by the cache memory. So there are multiple types of the cache memory: L1 cache, L2 cache, and the L3 cache. Now this is a generic cache memory organization, and that is used with equals to m equals to 2 power m unique addresses, that is 2 power b bytes, that is a valid byte that indicates whether or not the line contains meaningful information. T equals to m minus b plus s stack bits, that is used from the current block memory address that uniquely identify the block stored in the cache line. And in general, a cache organization can be characterized by the tuple, that is SEBM, and whatever the size, whatever the capacity of a cache CE that is stated in the terms of the aggregate size of all the blocks, that is included in this one, that is C equals to S into B E into B. And when the CPU is instructed by the load instruction to read a word from address of main memory, it tends to the address A to the cache. And the cache is holding a copy of the word at the address A, it sends a word immediately back to the CPU. This is the one valid bit per time, T tags per line. This is 2 power B bytes per cache block. This is set 0, set 1, set S minus 1. This is E lines per set. This is T bits, S bits, B bits. This is the fundamental parameter. This is the description of the parameter. S equals to 2 power S, that is the number of the sets, then E, number of the lines per set, then B, block size bytes. Then M equals to log to M, that is the number of the physical main memory address bits. Then the derived entity, that is M equals to 2 power M, maximum number of the unique memory addresses, then number of the S bits set, blocks offer set, tag bits. So these are used with the partitioning of the M, S index bits in A form, index of the S bits, and the first is set to 0, 1, and so on, that is stored with the cache memory. Next, direct mapped caches that are grouped into different classes based on E, the number of the cache lines per set, and the cache will exactly one line per set is known as the direct mapped cache memory. And these are the simplest both to implement, to understand how to illustrate some concept, how the cache memory works, or what is the usage of the cache memory, right? That is used to implement or illustrate the general concept about how the cache works. Suppose we have a system with the CPU register file in one cache and the main memory. For example, there are 3 files over there, and the CPU executes an instruction that reads a memory word W. It repeats the words from the L1 cache. Now, if the L1 cache has a cached memory, or if the L1 cache has a cached copy of the W, then we have an L1 cache hit, and the cache quickly extracts W and return to the CPU. Return to the CPU in the sense, why? Because everything is available in the cache memory. Otherwise, we have a cache miss. So that means if the data is available within the cache, that is a cache hit. Otherwise, it is a cache with a miss. And the CPU must wait while the L1 cache requests a copy of the block containing W from the main memory. And when the requested block finally arrives from the memory, L1 cache stores a block in one of the cache lines, extract the word W from the stored block, and return to the CPU. And the process, whatever the process that we are dealing out, so whatever the process that a cache goes through determining whether the request is a hit or a miss, then extract the requested word consists of 3 steps. One is a set selection, one is a line matching, one is a word extraction. Whatever the word extraction, whatever the data that we are using, that is used with the word extraction, that is used with the line matching, that is used with the concepts. Now the next is set selection in the direct map cache. So whatever the cache extract, whatever the cache involves, that is used with the set cache, that is the S index bits from the middle of the address for the W. And these bits are manipulated, interpreted as an unsigned integer that respond to a set of the numbers. And in other words, if you think of the cache as a one-dimensional array of the set, then the set index bits forms an array or index into this array. Then next is a figure that shows how to make the selection in the direct cache memory. Now next is line mapping. This is a set 0, valid tag cache block, valid tag cache block, valid tag cache block. This is a direct mapping cache memory. Now next is set selection in the direct mapping, and then word selection in the direct mapping, that is used with the cache memory, that is used with the cache bits, array of the line replacement, that is used with the cache selection or the word replacement or the word byte, whatever the word byte, whatever the data we are taking out, that word byte will be available within the data, within the T bits, within the 01110, that is used with the binary bits. Now this is the address bit, address, tag bits, index bits, offset bits, block number. Then this is a space for the example, direct bit operation, then direct mapping cache in the action. When the CPU performs a request or the sequence of the reads, remember that for this example, we are assuming that we are taking out the block, we are getting out the block over here that is used to read the data, that is used to make the reading of the data. And while this kind of manual simulation it is, yes, we may be tempted to skip it. In our experience, we will really need to understand that how the cache works or how it deals with the through of them with the data, how it deals with the data blocks. This is a set, then valid take block 0, block 1. And each row represents a cache line, and the first column indicates a set or the block of the sets, whatever we are using, that is kept in mind, provided for the convenience, and is not really good and is not, we can say, the best for the cache memory. And the next three columns represents the actual bits in the each cache line, whatever the cache lines that is available in the bits. Now this is the read word at the address 0, and since the valid bit for the bit is 0, then this is the cache memory that is available to miss the bits. To miss the bits, whatever the bits we are gathering out, whatever the data we are gathering out, that is used to the low level cache and store the bit in the set 0. Then the cache returns M0 concept of the or content of the main memory from block 0 to the newly fetched cache memory. Then read word at the address 1, read word at address 13, at address 8, at address 0. Then the conflict messes in the direct map caches, whatever the direct map cache that is available within the data within the time map. Then float dot product, float x8, float y8, float sum equals to 0.0 int I equals to 0, I is less than 8, I plus plus, sum plus x into I. That means array is multiplied with the array, whatever the array element, that is multiplied with the array elements only. And this function has a special locality that is also used with this one, that is used with the array content. Then this is the set associative caches. Then this is the main impact, that is the performance impact of cache. Just read out this thing, I will be taking out within 2 minutes, okay? Now the next part is what are the various performance impacts of the cache parameters. One is a mistake. Whenever the CPU wants to search for the application, if it is available in the cache memory, then there is a hit. But if it is not available in the cache memory, then there is a miss rate, so that the fraction of the memory references during the execution of the program or the part of the program that missed, it is computed as a misses reference. Then hit rate, the fraction of the memory reference that hit, it is computed as a 1 minus hit miss rate. Then hit time, what are the time that is taken to hit on the memory to search for the word and derive the word, that is known as hit time. The time to deliver a word in the cache to the CPU, including the time for the set selection, line identification, and the word selection. And hit time is on the order of the several clock cycles for the L1 caches. Then mix penalty, any additional time required because of the miss, and whatever the penalty that is taken out for the L1 miss is served from the L2, that is on the order of the 10 cycles, from L3 40 cycles, and from main memory 100 cycles. and optimizing the cost and the performance trade-off of the cache memory, whatever the cache memory we are taking out. That is a subtle exercise, or we can say that is used for the exercise that requires extensive simulation on the realistic benchmark, and therefore it is used beyond our scope, that is beyond our stone, or that is used beyond our we can say the scope. However, it is also possible to identify some of the qualitative trade-offs, then impact, that is very good trade that is available, impact of the associativity, impact of the right strategy that we have already done. Now, how to write on the cache friendly code. Is how to write in the cache friendly, or how to write in the cache friendly code. This is make the common case go fast, minimize the number of the cache messages in each inner loop, and that is equal such as the total number of the loads stored, loads with the better miss rates that will run faster. So int sum vac int I sum equals to 0, for I equals to 0, I is less than n, I plus plus sum plus equals to vi, then return sum. So that is used with the cache memory, that is used with the average size blocks, with the R0, with the V0. Now that is used with the putting on the loops, whatever the loop that we are putting up in this one, that is the size of the int4. SSC starts at 0 and destination starts at that 16, that is decimal one. That's aquarium that is used with this one. Then there is a false that determines the cache performance, whatever the cache performance that is available. Then the memory mountain, in the sense memory hierarchy, whatever we are using, that is also available over here. This is done, this is done. Yes, we have done with this. Oh, next chapter is linking that I'm going to start within the next class, that is the tomorrow's class. Okay, now if there is any doubts, any confusion, you can ask the doubt, because